Imagine waking up, stepping into your chilly bathroom, and having to physically shovel coal into this massive iron stove sitting right next to your bathtub.
Sounds awful, honestly.
Right. And then you strike a match, you get a fire roaring inside this metal cylinder, and then, you wait.
For a very long time.
Exactly. For like 45 minutes, just to get enough lukewarm water to wash off the dirt from yesterday.
Mm-hmm.
But, I mean, a little over a century ago, that was the absolute cutting edge of plumbing technology.
Yeah, it really puts our modern impatience into perspective, doesn't it? Today, you flick your wrist, a handle turns, and you just expect instant, perfectly heated water. You don't think about the fire, you just expect the result.
We totally want our conveniences to be, like, completely invisible. But the truth is, the second you demand hot water, you're kicking off this massive, highly calculated transfer of energy. So, welcome to the deep dive.
Glad to be here.
Today, we are pulling back the curtain on the engineering landscape hiding right behind your shower head. We're looking at a deeply technical engineering presentation. It's titled YF5.PDF, and it lays out the mechanical solutions for local and individual domestic hot water systems, or DHW.
Right, DHW. And our mission today is really to take those super dense thermodynamic and fluid dynamic concepts from the presentation and find the aha moments for you.
Because it's not as simple as just heating water up.
No, not at all. A proper DHW system has to operate under a very unforgiving set of rules. Specifically, this source outlines 5 golden rules.
Okay, let's lay out the stakes for the listener here. What are we actually demanding from our plumbing?
Well, first, it has to provide an uninterrupted supply of water at the exact right temperature, whenever you want it, in whatever quantity you need.
Which is already a huge ask.
Right. Second, it must allow you to easily regulate that temperature. Third, it has to meet extremely strict sanitary and hygiene norms.
Because nobody wants to get sick from their shower.
Yeah. Exactly. Fourth, it needs to be bulletproof-like, reliable, and really easy to maintain. And fifth, the kicker, it has to keep both the initial investment and the daily operational costs as low as possible.
I mean, I couldn't help but compare that list to running a perfect restaurant kitchen,
Oh, that's a good way to look at it.
Yeah, think about it. The meal or, the hot water needs to be fully cooked and plated the absolute second you walk in the door. It has to be the exact temperature you requested.
Right.
It has to be totally safe from a health perspective. The kitchen equipment can literally never break down. And on top of all that, the meal has to be incredibly cheap.
It's an engineering paradox, honestly. I mean, if you want a massive amount of heat instantly, you need an astonishing amount of power.
Sure.
But if you want it to be cheap and run on low power, well, you need a lot of time. That tension between time and power is what drove the entire evolution of hot water systems, starting with that coal-fired bathroom stove you mentioned.
Oh, yeah, the old Titan stoves. That detail from 1911 Berlin is just wild to me.
It really is.
The presentation describes this massive cylinder holding up to 200 liters of water with this vertical chimney running right up through the center of the tank. You literally had to build a wood or coal fire inside your house to heat it.
Yeah, and that 45-minute wait time you mentioned perfectly illustrates the physical constraint of what engineers call a low-power energy source.
Right.
A small coal fire, or even a modern low-wattage electrical element, simply does not have the intense, immediate heat transfer capability required to heat cold water as it rapidly flows past. The physics just don't allow it.
So you basically have to sidestep the power problem entirely, right?
You do. You have to slowly transfer that low-level energy into a physical mass over time. Basically, you bank the heat.
Like a savings account.
Exactly. That is the fundamental principle of a capacitive heater, or a storage heater. You're storing thermal energy in a physical medium, in this case, water for later use.
And we aren't shoveling coal into our bathrooms anymore, thankfully. But plenty of us still have massive capacitive storage tanks sitting in our basements right now.
Oh, absolutely. They're everywhere.
Let's unpack how the modern version actually manages that stored heat.
Yeah.
Because the source talks about how it relies on a concept called thermal stratification, which I found super interesting.
Yeah, thermal stratification is just a wonderfully elegant use of basic physics. When you take a shower, you're draining hot water out of your tank. But that tank isn't just emptying out, right?
Right, it's refilling.
Yeah, it's simultaneously refilling with freezing cold water from the city's main supply.
But wait, if you pour freezing water into a tank of hot water, shouldn't it all just instantly turn into a lukewarm, unusable mess?
You would think so, but water is surprisingly good at insulating itself, provided you use gravity to your advantage.
Okay, how does gravity help here?
Well, cold water is denser, so it's heavier than hot water. So the system is specifically designed to introduce the incoming cold water at the very bottom of the tank, usually through a specialized pipe called a dip tube.
Oh, I see. So it pools at the bottom, and because the hot water is physically lighter, it just floats on top.
It gets pushed up to the top, exactly, which is exactly where the outlet pipe is located. This stratification creates a distinct boundary layer inside the tank.
So the hot and cold don't really mix.
Right. It means you can draw 60-degree water from the top without it immediately mixing with the 10-degree water flooding into the bottom.
That's brilliant.
And the heating element, whether that's an electrical spiral or a heat exchanger coil connected to a boiler, is positioned down in that cold pool at the bottom, slowly bringing it up to temperature over several hours.
Wait, hold on. If the hot water is pushed to the top, and we're constantly applying heat to a sealed tank, I mean, water expands when it gets hot, right?
It sure does.
Where does the expanding pressure go? Does the tank just burst?
That exact problem is why engineers had to split these systems into two distinct categories: open and closed.
Okay, what's the difference?
An open system operates at normal atmospheric pressure. The tank is literally open to the air, usually vented right through a special tap over your sink.
Like it just drips.
Yeah. When the water heats up and expands, the excess simply drips out of the tap into the drain. It's totally safe, but because it's unpressurized, it can only serve one single draw-off point.
Ah, so a dedicated heater just for the kitchen sink, basically.
Exactly. A closed system, on the other hand, operates under the high pressure of your home's water main. It's completely sealed.
Which is what most whole house systems are, right?
Right. This allows the city's water pressure to push hot water throughout the entire house to multiple taps simultaneously. But to answer your question about bursting, because it's sealed and pressurized, these systems absolutely require specialized safety relief valves.
So they don't become bombs.
Exactly. If the pressure from the expanding hot water gets too high, the valve pops open and vents a little water to prevent the tank from rupturing.
Okay, but let's look at the reality of this closed system setup for a second. If I have a 300-liter tank of 60-degree water just sitting in my basement all day while I'm at work and all night while I'm sleeping, isn't that just a giant, incredibly inefficient radiator?
Well, yes. You are bleeding heat into the room.
Because I'm paying money to heat water, and that heat is just bleeding through the metal tank into my basement.
It's called standby heat loss, and it's a massive vulnerability in storage systems. You are continually paying a thermodynamic tax to maintain that 60-degree temperature against the ambient coolness of your basement.
A thermodynamic tax. I like that.
Right.
But I hate paying it.
Right. And it gets worse. If you have a large house, you might have a circulation pump keeping the hot water constantly moving through the pipes, just so it's instantly hot the second you turn on the upstairs shower.
So wait, I'm losing heat through the walls of the tank, losing heat through the walls of the pipes running through the house, and I'm paying for the electricity to run the pump all day.
Pretty much.
Why do we tolerate this? Why not just heat the water exactly when we need it?
Well, for decades, engineers simply didn't have a choice. Remember the power problem we talked about? The electrical grid in older homes just couldn't handle anything else.
The low power constraint.
Yes. If your energy source is relatively weak, you literally cannot heat water fast enough as it flows out of a tap. You have to use that tank to slowly charge up your thermal battery over hours, building up a reservoir for those brief, intense periods of demand.
Like when everyone in the house takes a shower at 7 a.m.
Exactly.
So it's an energy battery.
Right.
But as we just established, this battery leaks constantly. If you want to stop the leak, you have to completely eliminate the tank. Which brings us to the flow-through revolution, tankless heaters.
Right. Moving to flow-through heaters represents a massive shift in engineering priorities.
Yeah.
You're prioritizing efficiency and space over low-power constraints. But what's really fascinating here is that this shift wasn't driven entirely by energy savings.
Yeah, really.
No, it was heavily driven by the third golden rule we mentioned earlier, sanitary norms.
Hygiene.
Think about the environment inside a large storage tank. You have a massive reservoir of warm, sitting water. Bacteria, particularly dangerous ones like Legionella, absolutely thrive in warm, stagnant water between 25 and 45 degrees Celsius.
Oh, that's terrifying.
It is. By decentralizing the system, meaning you only heat the water as it physically flows through the pipe directly to the tap, you completely eliminate the stagnant reservoir, you remove the breeding ground.
And you fix the heat loss problem, too.
Plus, yeah, as you pointed out, you completely eliminate standby heat loss. You only use energy when the tap is physically open.
But the trade-off is severe.
Yeah.
Right? I mean, the math from the presentation on these pure flow-through units is just staggering.
It really takes a lot of juice.
To heat water instantly as it flows, taking it from a freezing 10 degrees coming off the street grid up to a comfortable 40 degrees for your shower in a fraction of a second, these small, wall-mounted devices require massive electrical spirals. They're pushing anywhere from 12 to 24 kilowatts of power.
It's an astonishing amount of localized energy to draw all at once.
Let's give the listener a sense of scale here, because 24 kilowatts is hard to visualize.
Good idea.
Go to your kitchen. A typical electric oven running at 400 degrees uses about 2 kilowatts. So pulling 24 kilowatts for a tankless water heater is the equivalent of turning on a dozen ovens all at the exact same second, just so you can wash your hair.
It sounds insane when you put it like that.
It does. If we're blasting that much power into the electrical grid every time someone turns a handle, how are we actually saving any energy or money compared to the old leaking tank?
Okay, so you have to separate the rate of energy use from the duration of energy use.
Okay, walk me through that.
The rate, the 24 kilowatts is incredibly high, but the duration is extremely short. The unit is only pulling that massive power for the exact number of seconds the tap is open.
Right.
A storage tank might use a much smaller 2-kilowatt element, but it runs for hours and hours to heat the water initially, and then it cycles on and off all day and night for years just to fight standby heat loss.
That's what adds up.
Exactly. The total energy consumed over a 30-day period is often much lower with the flow-through system, despite that intense spike during use.
Okay, that makes sense. But how does the machine actually manage that spike? If I turn on my sink to wash my hands, how does the heater know exactly when to fire up the dozen ovens?
The mechanical engineering inside these units is brilliant. They use a device called a Venturi tube to physically sense your demand.
The Venturi tube. Break down the physics of that for us.
Sure. Picture a straight water pipe inside the heater. Suddenly, the pipe narrows in the middle, creating a strict bottleneck, and then it widens out again on the other side.
Okay, got it.
When you open your tap and water begins to flow through that pipe, it hits the bottleneck. Fluid dynamics dictate that to get the same volume of water through a narrower space, the water speed must dramatically increase.
Oh, like putting your thumb over the end of a garden hose. The water shoots out faster.
Exactly like that. But here is the counterintuitive part of the physics. As the speed of the fluid increases through that bottleneck, its static pressure actually drops.
Wait, the pressure drops?
Yes. This is known as the Venturi effect. The water heater has a sensitive hydraulic contactor hooked up to this bottleneck. So when you open the tap, the water speeds up, the pressure drops, and that physical change in pressure pulls the contactor, instantly switching on the electrical heating elements.
Wow, so the water itself is physically turning the heater on just by changing its own pressure. That is incredibly elegant.
And modern units refine this even further with microprocessors.
Because of course they do.
Right. The processor reads the exact temperature of the cold water coming in, reads your desired output temperature on the dial, calculates how fast the water is flowing through the Venturi tube, and instantly modulates the power to the heating elements.
So it's not all or nothing.
No. If you only open the tap halfway to wash your hands, it won't blast the full 24 kilowatts. It might only use 6 kilowatts. It calculates the exact amount of energy required to bridge the temperature gap, ensuring absolutely zero energy is wasted overheating the water.
Which sounds like the perfect solution, except for one very real practical problem.
The grid.
Yeah. Picture your own breaker box at home. Most residential buildings, especially older ones, simply do not have the electrical infrastructure to handle a sudden 24 kilowatt spike.
They absolutely do not.
If you put pure flow-through heaters in an old apartment building and 3 people turn on their showers at the same time, you are going to melt the local grid.
You are. And engineers recognize that pure flow-through systems require infrastructure that simply doesn't exist everywhere. Most buildings can't support the massive power spikes, but nobody wants to go back to the giant, inefficient 300-liter tanks either.
So we need a middle ground.
Exactly. So the industry developed these ingenious hybrid solutions.
These hybrid systems are fascinating because they feel like cheating the physics of the problem, you know?
They really do.
You pair a high-powered flow-through heater with a tiny, heavily insulated accumulator tank, sometimes holding just 3 to 10 liters, and an internal pump.
It acts as a mechanical buffer.
Yeah, it's like having a small checking account for your daily coffee, but a direct line to the Federal Reserve for when you need to buy a house.
I love that analogy.
If you just turn on the sink to a trickle to rinse a cup, you're drawing water slower than the internal pump works. The system fills that tiny 3-liter checking account tank, heats it efficiently, and you draw your hot water from there. No massive power spike.
Right.
But if you suddenly crank the shower to full blast, demanding way more water than the little tank can hold, the system detects the massive flow. It physically bypasses the small tank entirely, opening valves that route the water directly over the main flow-through heating elements.
You get the best of both worlds. The stable, low-power response of a tank for the small stuff, but the infinite tankless supply for the big stuff.
It smooths out the electrical demand curve, making it totally manageable for standard building infrastructure.
Exactly. But there is another compromise system that completely rethinks how we handle hot water in multifamily apartment buildings. It's called the KTP, or apartment heat point.
The KTP. Let's work out why this is necessary, because a big apartment building changes the math completely.
It really does. Imagine a typical 30-story apartment building. In a traditional centralized system, you have a massive boiler down in the basement. It heats up hot tap water and then has to pump that water up 30 floors of pipes.
Which is a long way for water to travel.
And the entire time that water is traveling, it's losing heat to the concrete walls of the building. You need massive, heavily insulated pipes and complex circulation pumps running 24/7 just to ensure the person on the 30th floor doesn't have to wait 5 minutes for the cold water in the pipes to clear out.
It's a logistical nightmare and incredibly inefficient.
Huge energy waste. The KTP solves this by radically changing what gets pumped up the building. Instead of sending centralized hot tap water up 30 floors, the building only sends central heating water.
Wait, the dirty water meant for the radiators.
Right. The central boiler in the basement only creates one loop of superheated, chemically treated water. It pumps this up the building. When it reaches your specific apartment floor, it enters your individual KTP unit, which sits right in your hallway.
Okay, so what's inside the box?
Inside this box is a highly efficient device called a plate heat exchanger alongside a hydraulic mixing valve.
Okay, break down how the heat exchanger actually works without mixing the water. Because I definitely don't want radiator water coming out of my shower head.
Nobody wants that. A plate heat exchanger is made of dozens of ultra-thin, corrugated stainless steel plates stacked together. When you turn on your shower, clean, freezing cold tap water from the city main flows into your KTP and enters every other channel between these plates.
Gotcha.
At the exact same moment, the hydraulic valve detects your flow and instantly redirects some of the super hot central radiator water into the alternating channels.
So the clean tap water and the dirty radiator water are flowing right past each other in alternating microscopic layers.
Exactly. But they are separated by mere millimeters of stainless steel. They never physically touch, they never mix, but the thermal energy jumps instantly through the thin metal from the hot radiator water into your clean tap water.
That's amazing.
It heats your shower water instantly right there in your hallway, and then the cooled down radiator water loops back down to the basement boiler to be reheated.
Think about what this means for you, the listener, living in that apartment. You get programmable, instant hot water because the heat transfer is happening literally feet away from your bathroom, not 30 floors down.
Exactly.
You completely eliminate the bacteria risk because there is no stored tap water anywhere in the building.
Yeah.
But financially, this changes everything too.
Oh, absolutely. The building developer saves a fortune because they completely eliminate the redundant piping required to run a separate central hot water network up a skyscraper.
Less pipes, less money.
And for you, the resident, the KTP allows for incredibly accurate metering. Your specific KTP measures exactly how much thermal energy your heat exchanger pulled from the central loop. You are billed precisely for the heat you used, rather than splitting the cost of massive central boiler losses with the entire building.
It's a brilliant execution of those 5 golden rules we started with. It's sanitary, it's instantaneous, it allows for individual temperature control, and it drives down both installation and operational costs.
It ticks all the boxes.
We started this deep dive looking at a 45-minute coal-fired wait just to get a lukewarm bath in a massive metal cylinder. And we end up with Venturi tubes sensing microscopic pressure drops to trigger microprocessors and ultra-thin steel plates transferring heat from a central boiler in milliseconds.
The engineering behind just washing your hands is a century-long masterclass in balancing thermal physics, fluid dynamics, and energy efficiency.
The tug of war is real, but the mechanics make it invisible to us.
They do. But before we wrap up, there's an entirely different way to look at this evolution, and it's something I really want to leave you to ponder.
Okay, let's hear it.
We spent this entire deep dive detailing how engineers have fought tooth and nail for decades to move away from large, inefficient storage tanks. We've pushed toward instant flow-through heaters to save energy and space.
All right, we want to kill the standby heat loss.
Yeah.
Death to the storage tank.
Death to the tank. But zoom out and look at the broader energy grid today. As the world shifts dramatically toward renewable energy, specifically solar and wind, we face a massive new problem.
Which is?
Those power sources are highly unpredictable. The sun shines brightest in the absolute middle of the day when everyone is at the office. Solar farms produce massive spikes of incredibly cheap electricity at noon, but nobody is home to use it.
Sure.
Then the sun sets, everyone comes home, and the grid struggles to meet the sudden demand for evening showers and cooking.
So the power generation is completely out of sync with human behavior.
Exactly. We are currently obsessed with building massive, expensive chemical batteries like lithium-ion farms to capture and store that midday solar power. But consider the thermal physics we discussed at the very beginning. Water is incredibly dense and holds thermal energy remarkably well.
Oh, I see where you're going with this.
So could the inefficient thermal storage tank actually make a massive comeback?
Using water instead of lithium.
Yes. Instead of buying a $10,000 home battery, what if the simple, giant water tank in your basement was hooked up to the smart grid? When electricity is practically free at noon because of excess solar power, the grid commands your tank to turn on.
So it's basically soaking it up.
It acts as a massive thermal battery, soaking up all that cheap energy, heating the water up to 80 degrees. It just sits there banking the heat so that when you want a perfectly hot shower at midnight, you aren't pulling any new power from the dark, strained grid.
Wow.
You're just discharging the solar energy you captured 12 hours ago.
So the oldest, clunkiest technology we have, the giant tank, might actually be the key to stabilizing the modern renewable energy grid. It's no longer just a water heater, it's a thermal battery.
Exactly. Think about that the next time you turn the tap, expecting instant magic.
That is definitely something to mull over. Well, that's all for today's deep dive. Thanks for listening, and we'll catch you next time.